Okay, let's start. So today we will talk about the digital logic structures. So the transistor is the state-of-the-art component to build some computers. Here, transistor means CMOS transistor, and you can see that people try to integrate more and more transistors into a single chip. This is the state-of cell of the transistor. So you can see, due to the Moore's law, we have a lot of transistors on a single chip. The difficulty is that you need to make all the transistors on the same chip uniformly, so that the frequency is decided by the worst case. If this GPU can run at 1 GHz, at least the weakest transistor can run at this frequency. You can consider that why this is really difficult to fabricate a chip. Now only several company can do that. So the transistor is actually a switch, and by this simple switch structure, we can build different logic gates, and then we can use those logic gates to implement the more complex structures. So here is the switch structure. You can consider this part. When you open this switch, there's no electricity. This light will be off. If you close the transistor, then the light will be on. Because electricity pass through this switch. There are two types of so-called CMOS transistor. The first one is NMOS. So this is a NMOS. You can view it in the switch. This gate is the controller. You can control it. Close and open. So if you apply a 1 here, then you will close this switch so that the electricity can come. If you apply a 0 here, then the switch is open. No electricity can pass through this gate. Because we call it NMOS. It's actually friendly to this theory. GND means ground. So when it's connected to the ground to 0, then it can achieve better performance. The performance, I mean the switch frequency. The other type of CMOS transistor is the PMOS. You can see it's very similar to the NMOS. There are two differences. The first one is that if you apply a 1, open, there's no electricity. If you apply 0, then it's closed. This is the first difference. Because for the NMOS, if you apply a 1, if you apply 0, this is open. The second difference is that this PMOS is actually connected to the VDD, which is the power source. So when it is connected to VDD, it can have better performance. So typically we use PMOS to connect to the VDD and NMOS connected to the ground, to the zero. By these two types of MOS, we can build some simple logic gate like AND, OR, NOT. Again, we adopted the binary system. This is a 1 and then this is a 0. The 1 can be, the 0 is always small value, but the VDD is purely with your process technology. For the old physical process technology, like maybe 128 nanometer, the VDD is 2.9. Nowadays, for the 2 nanometer, 4 nanometer, or 8 nanometer, this is a 1 volt here. So by two types of CMOS transistor, we can build a network. And this network can implement some functions like AND, OR, NOT. And this network is actually consists of two components. One is so-called a pull-down network, which connected to the zero to the ground. So we use MOS. The other one is a pull-up network. It's connected to the VDD, so we use PMOS. So here is one example. This is a simple gate, which is so-called NOT gate in water. And you can see that there are two networks, pull down and pull up. It's very simple, just one single transistor in each network. And the pull down network is actually a MOS, which is connected to the ground, and pull up is a PMOS, which is connected to the VDD. And then this is a inverter. This is the logic operation, logic truth gate of the inverter. The output is actually the inverted input. You can see that. These two are opposite. So this is what will happen if we apply different value on the inverter. If the input is 1, then the NMOS is actually closed. And the PMOS is actually open. So the switch here is closed and the switch here is open. Then this output point is actually connected to the ground, which is a 0. So the output is a 0. This is the inverter function. This is 1, this is 0. So if we apply a 0 here, then the NMOS is open and PMOS is closed. And then the VDD can pass through this gate and to here. Then your output is 1. So this is why we have a 0 here, 1 here. Any question? So by simple 2 gates, simple 2 CMOS transistor, we can actually build a inverter. This is a NOT gate. The NOT gate is a simple. This is 2 input gate. Only when both A and B are zeros, the output is 1. Otherwise, the output is always 0. And this figure indicates the case when A is 0, B is 1. So when B is 1, then we need to look at these 2 gates. Since B is 1, then this is closed. This is open. And when we need to check A, then we need to look at the district and the district. Since A is 0, this is open, and the upper one is closed. Because the two PMOS in pull-up network are consecutively connected. If any of them is disconnected, is open, then the VDD cannot pass through. So VDD have no influence to the output here. However, the PMOS in the pull-down network, I'm sorry, the NMOS in the pull-down network is actually connected in parallel. So if anyone is connected, then the VDD can pass through and arrive here. So that's the reason why C is a 0 in this case. So only when these two values are both 0, we have these two gates closed, and the VDD can pass through to here. So we have a NOR gate here, and then at the output of the NOR gate, we add an inverter. Then this is a OR gate. So the structure here is just to add an inverter to the NOR gate. And this is the AND gate. You can see that in the NOR gate, the PMOS are connected sequentially. NMOS are connected in parallel. This is the opposite. PMOS are connected in parallel, and NMOS are connected in sequentially connected. So only when both A and B are 1, the output is 0. For all the other cases, the output are 1s. This is the AND gate. Just add an inverter to the NAND gate. Now we have 5 types of gates. So if you need a multiple input gates, for example, the 3 input gates, you can decouple it into, you can always build a 3 input gate by 2 input gate. So here we emphasize on the 2 input gate. So I will post a homework today. So by the AND or NOT gates, we can always implement any truth table here. The truth table can define a function. By 3 types of gates, we can implement all functions. First, we just need to pick up the rows which can generate a 1 output. And then we just OR these 2 rows. Each row can generate a 1 output. So you can try to implement this truth table by some logic gates, by AND, OR, and NOT. Most important law here, I think, is the De Morgan law. So you can see the De Morgan law like this. So this value is actually equal to A plus B, A or B. How can you prove that? How can you demonstrate it? So if you A or B, since these are zeros, so this is zero. If you have a one here, A or B will be always. So this is exactly zero. So the point of the De Morgan law is to prove this value is actually this value. The De Morgan law can help you to manipulate the NOT gate here, which means that you can use this structure to implement a OR gate. By this structure, you can implement a OR gate. We explained the two types of CMOS and then try to build 5 types of binary 2-input logic gates. And then we described that all the functions include only 3 of gates. And the De Morgan law. The last one is the De Morgan law, how to convert AND to OR by inverting, inputs and output. Now we have some logic gates and OR, NOT. So how can we build some combinational logic, more complex logic circuit, and even the sequential logic circuits? So I will explain this in the following slide. So this is a typical combination logic, which is if you have n inputs, in this particular case, we have 2 inputs, then this decoder can generate a 2 to n outputs. In this case, it's a 2 to 2, which is a 4 outputs. So each for because we have A and B, 2 variable or 2 inputs, then if you write a truth table, there are 4 rows in this truth table. Each row will generate a 1. So here each row can be represented by 1 output here. So if A and B are zeros, then this is 1. You can check these conditions. So by A and B, we can select 1 output here by setting it to 1. We have some circuit component which can do the opposite thing. For example, we have an n-bit selector and 2 to n inputs. But in this case, we can generate only 1 output. The output equals to 1 of the inputs, depending on the selector. For example, this is a 2 to 1. We can select 1 of these by setting the S. So if we select and if we set f to 2, then we may to speed. I'm sorry, in this case, 2 we select. If we set f to 1, then we select speed. And then we can do the addition by a full adder. Full adder means we have a carry in and a carry out. So we have a 1 bit carry in. The operand is A and B. So we have 3 inputs totally. And we have 2 outputs, which is a carry out and sum. And then we can write them into a truth table. Because we only have 3 inputs, so totally we have 8 rows here. Then this is the full adder circuit. This part is used to implement the C out. And then this part is used to implement the sum. They do share some components like this. This signal is actually goes here and goes here. Which means that although we have 2 outputs can share from circuit to generate some intermediate signals. If we have a multiple 1-bit full adder, then we can connect them together. We can connect the carry out of one full adder to another to the carry in of another full adder. So this is so-called a carry ripple adder. Because we have a 4 full adders here. So it's a 4-bit, multiple bit, 4-bit adder. It can give you 4 sum bits and 1 carry out. This is the simplest structure of the. You can see critical paths in the computation of this C out. So this critical path will decide the frequency of this circuit or the delay of this circuit. The adder is actually very complex combinational logic. The combinational logic means that there's no clock. And when you apply your input to this circuit, theoretically, immediately you can get output from this circuit. And when you remove your input from this circuit, then so this circuit has no memory. It cannot remember anything because there's no memory component in the circuit. But sometimes we do need some memory. For example, sometimes we want to do accumulation. The next, the result of the next cycle is actually dependent on the result is because you do the accumulation, add 1 number each time to the accumulated result. And there are such a lot of other like the ticket counter. or the vending machine or the traffic light. If you want to design a controller, you cannot use combinational logic. You have to use the sequential. In order to build a sequential circuit, you need some memory elements and the state machine. So this is one simple storage element. This is so-called SR latch. So this is a NAND gate, and this is the second NAND gate. The structure of the SR latch is very simple. Just two NAND gate. The R is used to reset or clear the element. Reset means you just plug it zero into the output. And S indicate you set the element, which means you write a 1 to the output. So if both R and S are 1, then the output can be either 0 or 1. So let's see that. So here the R is a 1. Assume the point A is also 1. Since this is a NAND gate, 1 and 1, which is a 1, we have a R gate here. And this is a 0. So this 0 will pass through here. So the point of T is also a 0. Then S is 1. This is a NAND gate. A and 0 is a 0, not a 1 here. So in this case, output here is 1. There are another possibility, which is that A is 0. So if A is 0, then the output here is 1. Because this is a NAND gate, A and 0 is a 0. If not, then this is 1. And this one will pass through here. Because this is a NAND, 1 and 1, and not, this is 0. So in this case, if S and R are all 1s, are both of them are 1s, then you don't know the value of out. So this is the reason why SR latch is not good enough to be served. Although you can set it and reset it, write 1 to it, write 0 to it. So if you have that unstable state, you can reset by assign a 0 to R. So if you want to set the cell, assume that we start with the output 0, then you need to change S to 0. For the SR latch, you can do the set, you can do the reset. You can also hold the value in the latch, but there is an unstable state. When you try to when you try to sign 0 to both R, you don't know the value of SR latch. There are another type of memory element, which is a so-called gated D latch. And this is the gated. Compared to the SR latch, it's more complicated because you have 4 components here. 3 of them mandate. This one is actually another. So the input of this NAND gate is actually important. Which means compared to the SR latch, this is more expensive because you have to use more hardware resource to implement this one. The good news is that you can remove that unstable state. So this gated D latch does not have that unstable state. So when we set a 1 here, we set a 1 to W, which is the right field. The output here will be the same as D, no matter D is 0 or 1. However, if we set a 0 to 1, the output just hold to the pure side of D. So you can see that this part is actually the same, but we add a new component to control. And this component can guarantee that there is no unstable state. So by the gated D latch, we can store 1 bit, which is the same as the D, which is the input. So if we have a multiple gated latch, create a multiple bit register. And then we also can connect all the WD of the gated D latch to 1 line. So this line is the writing able to the of the register. Only when WE is 0, you can change the value. I'm sorry, only WE is 1, you can change it. So you can see we can actually store this variable into the register. And this A will be 16 bits. You can consider it as a short variable in C. And you can use this expression to indicate the bit from 9 to 16 to 14. And this is the bit 0 to bit 2. You can also use this expression to represent. But in C language or C++ language, you cannot index. You cannot because in the state-of-the-art operating system, it's only byte addressable. You can each time the minimum unit of one access is one single byte. You cannot access one piece. You can read maybe the first 80 and then do some analysis, shift and all to know the value of these beats. And in the state-of-the-art memory system, memory is actually a consecutive space, which can be organized by into a k times m. So you have a k axis. K is actually 2 to n. And each entry has m bits. And in the modern system, operating system is a byte address, not a bit address. Particularly when you consider physical address and logical address, this is the logic. Only the logical address can be considered as a consecutive space. In the real DRAM, this whole array will be stored separately in different space. And typically one page will be stored in one part. And typically page is 4 kilobytes or 2 kilobytes. So this is how we store the data in the physical memory. And in the physical memory, you have followed max. And each m bit typically is stored in each row in the physical memory. Although we only have 3 cells here, but actually we need m cells. And totally there are k 2 to n rows. In this case, we only have 4 rows. So in this way, we can actually use this physical memory to implement this storage. But if we cannot, due to the cost, due to the fabrication issue, we may not be able to cover so large array, then we have to use multiple to store that large consecutive space. And Curious picture is just a example of one possible implementation of the memory. In the real case, the memory is more complicated because they want to reduce the transistor number in the memory. A lot of these so-called reference decoder mask writing enable will be shared by multiple arrays. So in the real memory chip, it's more complicated. But you can see the memory is very functionally the same. we have two types of a major memory. One is SRAM, the other is DRAM. SRAM is similar to these daily DRAM for a lot of transistors in one cell, but the density is low because one cell will contain maybe for the DRAM, it's just to use a capacitor to store the data. So the size of DRAM is smaller. DRAM is much denser than the traditional SRAM. The last piece of the controller is actually the state machine. You need to design a controller to control your combinational logic to read the data from a memory element and then do computation for this cycle. And at the end of this cycle, you write back the intermediate result and then read again in the next cycle, do the computation and then write back the results. So in this way, you can, do the accumulation, do a more complex operation. The combinational logic circuit here is the real worker, and the memory element is the place you can temporarily store your data, read your data. Again, for the combinational logic, you can consider the combinational logic as a secret key. Whether you can open the lock or not totally depend on your current input. If you do the right input in this cycle, then the lock can be opened. However, the sequential logic can remember what happened in the previous cycle. So the current output depends on the results in the previous cycle. The state is actually a state of the system is actually a summary of all the variables of the system at that particular moment. So there are several examples here. For example, a state of a basketball is the number of points, time remaining, and player cases. So the example of the lock has 4 different states. We call the 4 different states as A. For ABC, the lock is not open. Only for D, the lock is open. So with a multiple state, you have to remember only when the user completed this, then completed this. If the user did do nothing, then we can summarize the working flow of the lock in this state transition diagram. the same as the previous slides, we have a 4 state. And then we have multiple transition states connecting these 4 states. And attached to the transition, actually the user input is actually attached to the transition. For example, the R3 is actually a user input. If your lock is stayed in A, when the user gives you an input like R13, then you lock will move to the state B. So this diagram is used to describe the lock reaction, particularly when the user gives some inputs. So the finite state machine has to have a limited number of states and a limited number of external inputs and a limited number of external outputs. Then you have a clear description on the state transitions. And also clear definition of the output value. So typically, when the machine receives one input, it will move to another state. And the outputs are associated with each. So you can generate a different output by multiple states. Then we have the clock. The clock is used to control the finite state machine. The finite state machine can be triggered by the edge of the clock or by the level of the clock. So at the beginning of, typically it's triggered by the edge. So at the beginning of this edge of a clock, I should say, the state machine make a transition based on the input and the current state. So which means that at the rising age, you actually read some data from the register. And then at the end of this clock, at the falling edge of the clock, you need to do the write. Write something into the register. The finite state machine is actually can be implemented by truth table 2, which is similar to the logic gate, but more complex. We can use a master-slave flip-flop to serve as the storage of the finite state machine. You can see that the master-slave flip-flop is two gains in that. It's the first one, and this is the second one. And these two D latches are actually controlled by one clock. When the clock is high, time is one, the value of clock is one. You have the right enable here is zero. So no data can be written into this. But the right enable here is one. Then the value of here can be passed through this one here. When the clock is low, the right enable here is low, so nothing can pass through this. The second part of this master slave, or I should call it a slave. But this one is high. So the new input can go through this part. So this is how they read and write value based on different values of clock in the same cycle. In one cycle, when the clock is high, they do something, and then when the clock is low, they do something. So you can see that the 2D latch is used to record only one state bit. The number of storage elements is actually decided by the number of states. For that lock example, it requires 4 states. For more complex applications, much more states actually. Then this is another example to design a traffic sign. We have different cases, no lights, 1 and 2, these are on and these are repeat. So in the first cycle, nothing is on. These 2 on, 1 and 2 on, these 2 on, and these 4 on, and then everything is on. Then return to no lights on. So this is the finite state machine to control that. And we have 4 states here. And we also have input. The input is on and off. Again, you can generate a truth table to describe that finite state machine. Because we have 4 states. The first state bit is state S0. The second one is S1. And then we also have input 1 and 0. So totally we have 3 inputs. So like that, there are 3 inputs. The output is where the transition go, which is should be a valid states described by the value of to distinguish them. You can go through the finite state machine and complete it like this. This truth table is used to describe the transition. based on the current state and the input, where the finite state goes in the next cycle. And in the this is the when this truth table is used to generate the light. We have 5 lines. So in order to control these 5 lines, we need a 3 bit to do that. 2 to 3, which is 8. So 8 is larger than 5. So this is enough. If we only have 2 bits here, we can only control 4 lines here. First, we need our line 5. After you complete this part, you can have this truth table too by reading the transition table. So eventually you can get this circuit based on the previous 2 truth tables. You can view the traffic light controller as a computer because the traffic light controller actually try to implement some functions, while your computer is actually try to implement a more complex function. They are similar. In this lecture, we talk about the combinational logic, including these examples, decoder, max, ALU. And in your real computer, you will also have components, but there's no states. These combinational logic are just some workers which can help you to do some job within one cycle, within one clock. We also introduce some sequential, including finite state machine. These are components which can control those workers to do the more complex job. Any question? We have 2 types of CMOS. NMOS is sensitive to the 0, and the PMOS is sensitive to the 1. So this is NMOS, and this is PMOS. By the pull down and pull up network, we can form a gate. And then typically we use NMOS in the pull down and PMOS in the pull up. And any other questions? So if no question, we can stop today. Thank you very much.